Hi, my name is Abby Koenig, and this is my lab 3 for Physics 2211 on black holes. So the steps for this lab basically consisted of 2 parts, along with answering some questions. For part 1, the purpose was basically just to find the mass of a black hole using a computational model, in which the system was the star and the surroundings were the black hole along with space. And for part 2, the purpose was to calculate the initial velocity of a spaceship so you could fly incredibly close to the black hole without actually crashing on the planet or the black hole. The system for this was the spaceship, whereas the surroundings were the black hole and space and the planet. Then I had to answer some questions that will be talked about at the end. So the key concepts for this were basically the same for both part 1 and part 2, just had to acknowledge Newton's second law of motion, which explains the relationships between the net interaction between systems and surroundings, along with the changes in momentum of the system. I also had to look at the force of gravity formulas, which says that the force of gravity is equal to big G times both masses over r squared times r hat. So looking forward, when I applied all these key concepts, I was able to find the total net force to be 8.53 times 10 to the 28th, with the parallel component being 2.3 times 10 to the 28th, and the perpendicular being 8.2 times 10 to the 28th, all in newtons. The mass of the black hole was 1.31 times 10 to the 34 kilograms, which was found at the end of part 1. So looking at the code for part 1, when I had to find the mass, most of the stuff on the left side of the screen did stay the same. There wasn't much that I had to change in that region, but in the actual calculation loop itself, I had to kind of look at the initial and final velocity formulas so that I could plug those into the momentum formulas, then plug both the velocity and the momentum initial and final formulas into the delta V and delta P formulas, thus so I could find the net force, which is equal to the derivative of P, which would be change in P over change in T. Then how to calculate, the parallel change in P and find the parallel force along with perpendicular force, which was fairly easy to do once Newton's second law was applied. Lastly, I had to calculate the mass of the black hole, which I used by deriving from the gravitational force formula, where you have net force times the initial position minus the original position, all divided by the mass times big G. So then for part 2, when we were flying close without actually crashing, the initial conditions were mostly the same, except I did have to sub in for the mass that I had found, along with editing the lines of the ship's speed in both the X and Y direction that I had wanted it to be. Then looking at the calculation loop, there were 2 main parts to this, in which I had to find the net force on the planet along with the net force on the spaceship, which basically just consisted of combining the black hole's gravitational force on the planet and the ship's gravitational force on the planet, and then same for the spaceship. Then when we were actually making things move, we had to apply that P is equal to F net times delta T, which gave us the planet's velocity and planet's position and the updated position and velocity formulas. Same thing we had to do with the ship and apply all of these into the brake conditions. So for what does it mean when discussing how the net force and its parallel and perpendicular components differ from the rate of change of momentum and its parallel and perpendicular components? There aren't technically any differences between these 2 components. The main applicable difference is that the rate of change of momentum can be calculated without knowing the mass of the black hole, whereas the net force cannot. And this kind of led me to a possible source of error, which implied that there could be some inaccuracy in the estimation of the average mass of black hole, which meant that the net force wasn't positively correct if there were possible errors relating to the mass of the black hole. Then when looking at what if, I had to find the initial velocity of the spaceship so that it could enter an orbit around the black hole without actually crashing. So for this, I had to acknowledge the fact that the direction vector of the initial velocity would have to be parallel to the force of the planet. And also the initial velocity would have to be greater than the velocity of the planet itself. So this was all found through trial and error, and I finally had found that the initial velocity for my computational model was estimated to be -9 times 10 to the 5th meters per second for the x direction, and 1.3 times 10 to the 7th meters per second for the y direction, and 0 for the z direction. Thank you for watching, and goodbye.